Yes, please start, Ghazi.
Hello, my name is Ghazi. Today I'll present my thesis. The title is An Independent Set of Image Quality Tests for Cone Beam CT. Investigation of Catphan Accuracy, Evaluation of the Accuracy of the Existing Software and Method. First, I would like to thank my supervisor, Pejman, Zaid, and Mahsheed. Radiation therapy has always required data from imaging for treatment planning as well as execution. When the treatment target is not located on the surface, inspection and visual confirmation are not possible. In early image guidance, skin markers and bone structure were used for image patient positions. However, these are associated with intrafractional motion uncertainties. Treatment planning starts from simulation to the delivery of the plan. However, the position of the patient is different, which lead to differences in target positioning. The accuracy of dose distribution and the target and patient position require proper use of image guidance technique during the radiotherapy. Image-guided radiation therapy defined as the use of on-board imaging prior to the treatment to guide patient position and set up as well as updating the plan for adaptive radiotherapy. It decreases the side effect as well as improving the outcome. It's highly accurate and precise treatment. Error and margin in radiation therapy, mechanical uncertainties such as couch and motion, gantry motion, geometrical uncertainties, patient positioning and target motion, geometric uncertainty related to quality assurance. However, IGRT deals with geometrical uncertainties. Cone beam Cbct, the most recent advancement in volumetric imaging IGRT. Using Cbct prior to the treatment session, a full CT scan of the patient is acquired in less than 2 minutes. The CT scan is registered to a reference CT data to facilitate the accuracy of patient position and to the treatment beam isocenter. Kilofolded Cbct, the most common application of three-dimensional cone beam CT. Based on a tomographic image obtained at the time of radiation therapy, capable of producing radiographic and fluoroscopic images. Quality assurance for Cbct-based IGRT. The primary goal for QA program is to ensure the imaging system performance characteristics do not differ from what has been established as commissioning time. Image quality for Cbct. The image quality of KV-Cbct system is significantly influenced by the characteristics of this technology, such as the pixel size and voxel size, as well as the geometry of the cone beam. The larger the cone beam angle increases the scatter signals, which in turn decreases the contrast of soft tissue and the accuracy of CT number, as well as increasing the noise. The aim of this project is to investigate the accuracy of commercial software and methods, namely BIPS Pro, and develop an in-house image quality software. The material, KV-Cbct tomography. For an onboard imager, 3 units have been used, Acacia and Jar and Turat. The 3 units were accepted and commissioned before being clinically used. Catphan 604 Phantom. It's a cylindrical phantom 20 centimeter diameter. It has 4 scan sections for different test model. Scan section 2 for slice thickness with 2 pair wire ramps and 10 insert target for 100 unit consistency tests, as well as low contrast visibility and 4 holes for geometrical accuracy. Scan section 1 for spatial resolution. Scan section 3 for low contrast measure. Scan section 4 for uniformity test. Software used in this study, BIPS Pro to investigate its accuracy, MATLAB to develop the software, other software to validate the result, IQ work, and MJ. Method to investigate the accuracy of BIPS Pro, 3 units were used to scan the Catphan Phantom in 4 different protocols: head, pelvis, and spotlight and thorax. The scanned image were reconstructed and exported as DICOM files for offline analysis. The Cbct modes the tube voltage for head 100 and for Belfast spotlight thorax 125 kV. The current is tube current is 15 for head and thorax and 60 for Belfast and 12 for spotlight. The fan type, full fan for head and spotlight and half fan for Belfast and thorax. The slice thickness 2 mm for head and spotlight and 1.99 for Belfast and thorax. The image parameter measured by both software are the uniformity and noise, Hansford unit consistency, slice thickness, geometrical accuracy, low contrast visibility, spatial resolution, and low contrast detectability. The investigation in two parts. The first part to analyze the image quality by both software. The second part to analyze and compare the accuracy of PIPSO with the study software. The first part done by comparing the results of the two software to a threshold or expected value. The second part, as the result of the image parameter, a series of numerical value needed to be compared against the theoretical or expected value, we use the root mean square error. Then we compare the root mean error for both software. Image parameter scan section 2 has slice thickness. The image shows the two pair file ramp, one oriented to the x-axis, one oriented to the y-axis. The slice thickness was calculated by determining the full width at half maximum of the wire ramp. By plotting profile around the wire ramp, we determined and averaging the profile and convert the pixel to millimeter, we determined the full width half maximum, then multiply it by 0.42. The measured slice thickness should be within 1 millimeter of the nominal value. Geometrical accuracy. The primary goal of this test to ensure the beam isocentral imaging system are in agreement. 4 holes were used for measuring the geometrical accuracy. These holes are 3 millimeter diameter and equally distant 15 millimeter diameter. The measured distance should be within 2 millimeter of the reference value, 50 millimeter. For Hansford unit consistency, scan section 2 has 10 insert target with non-Hansford unit value established at commissioning time for each unit and each protocol. The mean Hansford value of this target was measured and compared it to expected value. The measured value should be within the tolerance level 50 Hansford units. Low contrast visibility. The goal of this test to check the ability of the system to differentiate between objects with almost similar density. The manufacturers suggest low density polystyrene and polystyrene. By measuring the mean and standard deviation of these two targets and apply this equation, we find the low contrast visibility. For spatial resolution test, the modulation transfer function was used to assess the spatial resolution of the Cbct system. A method reported by Durag et al. By following equation. The MF referred to the region of interest on the line pairs. The MO obtained by the following equation. The absolute difference between CT1 and CT2, which refers to the number of pixels of CT values in the high contrast model and CT2 and the water. Scan section 3, low contrast model. For low contrast detectability is defined as the scanner ability to precisely distinguish objects with intensity similar to the background value. It's mathematically similar to contrast to noise ratio, but it's different as low contrast detectability has a detectability limit that allows the result to be true or false, detectable or not. The range limit detection is normally in the range 329 standard deviation to 5.5 standard deviation. In this study, we used 329 and PIPSO used 4. At first, we used 4 as PIPSO, but we couldn't detect any targets. So we changed it based on our experiment. We changed it to 3.29. It's calculated by the following equation: the mean target, the difference between the mean target, and the mean background divided by background, the threshold 3.29. The result is reported by two scores using the contrast group: the percent detected, the number of targets with respect to the total target within the contrast group, and the contrast detectable target, and multiplied by the diameter. Scan section 4, image uniformity and noise. The Catphan contains CTB 729 uniformity housing test model, which is made from a uniform material. Uniformity and noise were evaluated as the mean and standard deviation value of the CT numbers within this region. The diameter of this study, 20 millimeter. BIBS Pro used the shape, rectangular shape, unknown size. Result and discussion for geometrical accuracy. An agreement within less than 5.5 millimeter for all units obtained by both software. The study software, in terms of root mean square error, the study software has more root mean square error than BIBS Pro in 7 different protocol units from 12. The overall root mean square error shows slightly in favor in this study by 0.23 millimeter compared to 0.24 millimeter. For slice thickness, for head and thorax protocol, an agreement with less than 0.5 millimeter obtained by both software. For pelvis protocol, an agreement within 0.5 millimeter for thorax obtained by both software. However, for JARA, an agreement with 0.6 millimeter obtained by this study and less than 5.5 millimeter for BIBS Pro. For Acacia unit, an agreement with less than 0.5 millimeter for this study, while for BIBS Pro, 0.5 millimeter. Spotlight protocol, an agreement with less than 0.5 millimeter for JARA by both software. For Acacia and Thorat, an average 0.7 millimeter by this study, while for BIBS Pro, significantly lower accuracy on average 1.1 millimeter. The study software has smaller root mean square error than BIBS Pro on 8 different protocol units from 12. The overall root mean square error shows a significant difference root mean in favor of the study, 0.35 millimeter compared to 0.52 for BIBS Pro. And for unit consistency, the software has smaller root mean square error than BIBS Pro on 7 different protocol error from 12. The overall root mean square error shows a slight difference of root mean error in favor of BIBS Pro. That's due the measurement of head and Acacia were less accurate by this study due to the fact that Teflon measured by this study deviate by 89 Hans fluid units. These are the measurement for Acacia unit by both software. However, we did further investigation using MJ. We used different size of region of interest. However, none of the reported value has come to the tolerance level or near to the reported results by BIBS Pro. For low contrast visibility, head protocol, almost identical for JARA, 3.15 for BIBS Pro, and 3.16 for the study. Where for Acacia, high contrast by this study, 2.39 compared to 2.54. And Thorat, high contrast by BIBS Pro, 2.12 compared to 0.37 for this study. For pelvis protocol, identical for Acacia units, both software, whereas for JARA, significantly higher contrast by this study over BIBS Pro. For Thorat, BIBS Pro more accurate than the study, 0.81 compared to 0.97. For Spotlight protocol, for Acacia unit, PIPS-Pro indicates the failure of the tests, whereas the study indicates otherwise. We measure by 1.606, whereas PIPS-Pro 1.218. For JARA, roughly comparable, 0.91 for Pro and 0.39 for the study. For TORAS, 0.29 for the study and 1.2 for PIPS-Pro. Thorax protocol, significantly higher accuracy by the study, 0.91 compared to 1.4. For JARA as well, 0.49 for the study compared to 0.29 for PIPS-Pro. More accuracy for PIPS-Pro for TORAT, 1.046 compared to 1.11 for the study. For the spatial resolution test at the protocol, from the graph, it can be seen the PIPS-Pro more accurate than this study. However, we have implemented 3 methods for measuring the spatial resolution. None of the methods has come to the close to the accuracy of PIPS-Pro. It's highly accurate in this study, even in previous protocol and other protocols as well. For low contrast model, Belvis protocol, Acacia, the study was able to detect 2 mm target at all contrast level with 100% detection, while for PIPS-Pro at 1% contrast level, 50 mm diameter target was detected, and neither at 0.3 nor at 0.5 contrast level any target were detected. For JARA unit, this study was capable of detecting a 2 mm target at all contrast level. PIPS-Pro only for JARA, 50 mm target at 1% contrast level was detected. For TORAT, this study was capable of detecting a 2 mm target at all contrast level. The target of 60 mm diameter was detected at 0.5 and 1% contrast level. For Spotlight protocol, Acacia, PIPS-Pro were unable to detect any target at any contrast level. However, for this study, was able to detect a 2 mm target at all contrast level. While for JARA, the study detects again a 2 mm target at all contrast level, while PIPS-Pro 4 mm target was detected at 1% contrast level. PIPS-Pro, the lowest detected target is 50 mm at 0.5 contrast level and 0.5 mm at 1% contrast level, while for the study detected 4 mm at 0.3 contrast level and 3 mm at 1 and 0.5 contrast level. For uniformity and noise, for JARA, both software indicate the failure of the unit. Both this study reported 43 handful unit, while for PIPS-Pro indicate 47 handful units. Both indicate the failure of the units. For TORAT, the result by both software within the handful unit, within the tolerance level, 40 handful units. While for Acacia, both software indicate the result to be within the tolerance level, 40 handful units. However, the largest value was recorded by PIPS-Pro for Centeroy, 37 handful units, while for this study, minus 12 handful units. We did further investigation by IQ work. It's still a larger deviation than this study and PIPS-Pro, minus 26. We did it in image J, a different size and different shape of the rows, but none of the value indicate any close value to what measured by PIPS-Pro. Conclusion, PIPS-Pro show its ability in terms of accuracy within the tolerance level. The result has clearly shown that software can practically be trusted for QA, even though the result has shown PIPS-Pro relatively lower accuracy in terms of geometrical accuracy and slice thickness, as well as low contrast detectability. These parameters only deviated by a few margins can be ignored. Highly accurate for measuring spatial resolution, For future suggestion, we suggest to be extra protocol to be included. However, this study software able to include extra protocols, but due to the limitation of the presentation, we couldn't. As well as for CTQA based on Catphan images, the study software capable of measuring Catphan images for CT, but the conversion with BIPS Pro impossible because BIPS Pro use different phantom for CT images. Investigation for potential application of Cbct for adaptive radiotherapy. Acknowledgement. First, I would like to thank my father for supporting me financially and emotionally, and Pejman for his patience and guidance, Zaid and Mahsheed, Tegan, and the Director of Physics Department at Prince Abdal University, Dr. Tariq, and the person who inspired me to be medical physics, Dr. Farsamaya. Thank you for those, and for the Saudi Cultural Mission for the scholarship. And questions?
Yeah, Ghazi. Any questions from Ghazi? If you have questions, you can talk loud or you can come over here. So Mario.
Hello, Ghazi. Thank you for your talk. I really enjoyed it. Can you hear me?
I can hear you.
Thank you. Would you mind going back to the results of where you showed the MTFs? Oh, he froze. Sorry.
Can you hear us? Go to MTF slide.
Oh, sorry, I can't hear you, Ghazi.
Can you hear me?
Yeah.
Ah, yes, perfect. So the MTF slides. So you might have already explained it, but I might have missed it. So apologies if I did.
Which, the results
but
or the message?
Yeah, thank you. So, yes, sorry if you explained it already, but could you please explain again the graphs?
Okay.
The MTFs look quite differently, and what was the reason for this?
Okay, from the graphs, the red colors for BIPS Pro measurements, the blue colors for this study measurement. It's clearly BIPS Pro more accurate than this study. Actually, I have implemented 3 methods for spatial resolution. None of the results has indicated any close value to the accuracy of BIPS Pro. Clearly, maybe I have mistaken implemented methods for sure there, but I don't really know the reason behind that. I don't know what was going wrong.
Maybe they use different calculation for measuring
Yeah.
MTF, which is unusual.
Yeah, or PIPS for us, the manufacturer wants to promote good answers.
Right. Yes, that's the only thing. So we just want to check the quality of PIPS because it's a black box.
Yeah.
We don't know what's going on inside. Just want to have some sort of individual or investigational validation for the CAN system and see if it's close to validation or doing something extremely wrong.
Like his method shows that he calculated MTF correctly. Right. It's just the difference it would be interesting to further investigate. But thank you, Ghazi, for answering my question.
This is Munir, Ghazi.
Hi, Munir.
Hi, Ghazi.
How are you?
Good. How are you?
Good.
Just a quick question about the HU value in Acacia. So just was wondering, like, if you go to the H, especially for the head protocol.
Yes.
It seems like your studies and PIPS Pro was okay. Yeah, no, if you go back, yeah.
Let me show you the full results for it.
Yeah, when you see the H value only for the head in Acacia wasn't agree with the others. Is any reason for that? Or did you repeat the measurement several times in Acacia, or just was done once? Or
No, I did it many times. I did it many times. This value is wrong, 65.95. I did it many times. I'm 100% sure. Nothing wrong with my measurement. Something wrong with BitPro. I did it by IQ work, and I did it by MSJ. None of the value even close to the tolerance level, even not too close to BitPro. The highest value is 1040. So I don't know why is this value is reported.
All right, that was my question. Okay, thank you.
No worries.
Thanks, Ghazi. I was just going to ask about the differences between the cone beam systems. I mean, they're all from the same manufacturer. What would cause differences from one cone beam system to the next?
You mean from unit to another unit?
Yes. Yep.
You know, every unit, its stability, it's different than other units. With the time, the stability of the unit degrades from what have been established from the baseline at commissioning time. So there is absolutely there is different baseline value for each unit and each protocol.
Okay. So do you know of those three, which is the oldest unit?
Actually, I don't have the ages of the units.
Mm-hmm.
I should have asked Mahsheed, but I didn't.
No worries. Thanks.
No worries.
Happy. So the other thing I need to mention, Ghazi performed all this programming and the things by himself. He was so self-motivated, never asked for any help. All crazy programming for image processing and assessment was himself. He didn't mention, was a bit humble to say in the presentation, but it was to us, he never asked us for any help, just created the commercial software, like commercial software by himself. Thanks very much, Ghazi. It's great.
Thank you.